All right, physics, welcome to your next lecture. Here we are in Chapter 5. We're going to be doing a lot of the same things that we did in Chapter 3 in Chapter 5, with the exception that we are looking at motion in 2 dimensions now. So you analyze the x and the y independently and then combine them to see what the resultant motion is. Okay, and that'll become clear with the examples we go through in a moment. First, we need to know that displacement in 1 dimension and displacement in 2 dimensions is basically the same idea. When you did displacement in 1 dimension, you had to subtract the final and the initial position to get the displacement that happened. Here you subtract the final and the initial vectors to get the displacement. You wind up doing the exact same thing. It's just that you have to look at the vectors with their components and do the subtraction that way. Okay, so we're going to do several examples in this vein, and I hope by the end you will understand it very, very well. Here's just a picture of what I'm talking about. If you have a vector first that takes you out to location P here in the diagram, and then you change directions, and you now are traveling along this vector to location Q. If you were to say, well, what's the displacement between the two? It's what would it take to go from P to Q? So you would subtract P minus Q, you would get a vector that looks like this. And that would be exactly the line that it takes to connect P and Q. So there's several examples along this line in your book. If you have any questions about that overarching concept, feel free to post a question in the comments field below or see me in class tomorrow. Just another picture of that. If you were to go here, and then you were to go here, and the question is, what's your displacement between those 2 points? Even though you traveled through this squiggly line, your displacement is always a straight line. If you subtracted this vector minus this vector, you would get this vector, and that would show you your displacement over time. Okay? When we travel in 2 dimensions, the x and the y are independent of each other. So just an example here, if you're up on a hill and you fire a cannon, the cannonball is going to go up for a little bit, and then it's going to go down, and the y direction is going to be influenced by gravity. So if you see initially it's got a certain portion of its vector component that's going up in the y direction, that gets slowed down because of the acceleration of gravity. Eventually there is no y component, and it hangs for a minute in midair at the top of its flight. And then gravity starts accelerating it downward. So you will see an increasing velocity downward in the y direction. But notice that while the y velocity is changing, the x velocity stays the same, because until you take physics with calculus in college, we can ignore things like air drag and wind resistance. So we just assume that the x horizontal composite of its velocity stays the same. So that is the same all the way through the graph. So the x and the y are independent of each other. They don't influence each other. And we'll see a couple more examples along those lines here soon. Okay, so projectile motion, that is the simplest and most direct application of motion in 2 directions. You shoot something up in the air, and you want to know how long does it fly, how high did it go, how far across the ground does it go, things of that nature. And so ballistic motion is what we're going to be looking at here. So ballistic motion, we're tracking a projectile's flight, okay? Remember that you can use sine, cosine, and tangent to analyze the different aspects of the composite vectors that are there. And we did a lot of that with Chapter 3 and 4. So hopefully you're getting a little bit more comfortable with those. We're going to do several more examples of that here. You always want to track the vertical pathway first, because the vertical pathway is what's going to give you flight time. The vertical pathway is what is slowed down by gravity and then accelerated back to the Earth. So tracking the vertical aspect of the pathway will tell you how long the object is in the air. And then once you have the travel time, you can use that same travel time at the horizontal velocity to figure out the range, or how far the thing flew. Okay? And we can always assume that the horizontal velocity is constant. We can ignore drag in high school. And so that's a little benefit of not having taken calculus yet. So there you go. So our first example, we have a collegiate javelin thrower here. and she wants to throw her javelin as far as she can. That's the point of being a javelin person. And so she launches the javelin, and the initial velocity as it leaves her hand, and I actually looked this up because I didn't know how fast javelins go, but the competitive javelin speeds are right around 36.9 meters per second, which is pretty stinking fast. They throw these things at around 60 miles an hour, so don't want to get hit by one of those. But 36.9 meters per second, and the initial launch velocity here of the javelin versus the ground is 50.3 degrees. Okay, and that's a positive measurement because we're going up from the horizontal. Okay, 50.3 degrees above the horizontal, 36.9 meters per second. So we're going to do a couple of things. We're going to calculate the vector components of the initial velocity. So of the initial velocity, what is the y and the x component? Okay, and then we're going to use 9.81 for the acceleration of gravity, and no other forces. We're going to ignore wind and drag and all those other things. And we're going to determine the flight time of the javelin, how long is it in the air. And then we're using the flight time, we're going to determine the range of the javelin and how high it got. So that's what we're doing. First, let's analyze this vector. Okay, so we're going to calculate the vector components of the initial velocity. The initial angle is 50.3 degrees. And so that's the angle here. This is the adjacent leg, so I can use cosine on this side. So the hypotenuse times the cosine of theta gives me 23.57053 meters per second. That's the horizontal component. And again, I'm using way too many decimal places here because I don't want to round until the end. We want to correct for sig figs at the end. You don't want to round throughout. That creates rounding errors. Okay, and then here, here's my degree. Now looking at the vertical component, if you were to draw the triangle over here, that's the opposite side, so I use sine. Okay, so the hypotenuse times the sine of theta gives me 28.39084 meters per second in the vertical. So it's going a little bit faster in the vertical than it is in the horizontal, and you can see that that makes sense because the javelin is tipped a little bit more than 45 degrees. It's at 50.3 degrees right now. Okay, so more up than out is how she's launching this javelin. Okay, so now I have my vector components. I need to determine how long it's in the air. Okay, we need to realize that projectile flight is symmetrical. So the same amount of time that it takes the javelin to leave her hand and peak is the amount of time that it'll take from the peak to the ground. Projectile flight is symmetrical on both sides, the upward and the downward component. So the amount of time it takes for gravity to slow the ascent of the javelin to 0 meters per second is the same amount of time that it'll take it to fall back to Earth. So we're going to use the equation of motion here, and we just need to see that the final velocity in the y direction is the initial velocity in the y direction plus the acceleration of 9.81 meters per second downward, so it's negative 9.81 meters per second, times the amount of time that it took. We don't know how long it took, that's what we're solving for. Okay, so 0, because my initial velocity is when the upward momentum stops, or the upward velocity stops. Okay, so 0, my initial upward velocity, that 28.39084, plus my negative 9.81, that's the acceleration of gravity towards the Earth. Notice the opposite sign because initially it's upward motion, and then the final is going to be downward, times an unknown amount of time. So all I have to do is solve for delta t. So I'm going to subtract this over and then divide by negative 9.81, and I get 2.89407 seconds. Again, a ridiculous number of decimal points because I don't want to round yet. Okay, 2.89407 seconds, that's how long it's in the air. That's how long it takes to peak. Okay, so if that's how long it takes to peak, how long is the entire flight? Well, it's symmetrical, so if it's that much time going up, it's also that much time going down. So that means that if it takes 2.8940 seconds to go up, it'll take just as long going down, making a total flight time of 5.78814 seconds. So she launches the javelin. It takes almost 6 full seconds for it to land These things travel a long ways. Okay, so that's my amount of time. I'm going to leave that up where I can grab that conveniently in the future. Okay, I'll need that. Now, using the flight time to determine the range of the javelin, we're going to do that next. Horizontal velocity is assumed to be constant. In high school, congratulations, you don't need to worry about it. So we just need to use velocity and time to calculate the displacement in the horizontal direction. So displacement in the x direction is velocity in the x direction times the amount of time. Displacement in the x direction then is this velocity, which I got from here, right? That's my x direction velocity, times a certain amount of time. That's how long it was flying. So this number times this number gives me a displacement in the x direction of 136.42959 meters. That's how far she threw the javelin. That's a very, very long throw. Okay, that's well over a football field. So it's a very, very strong throw. Okay, so there you go. That's how far it went in the x direction. Not done though. I want to know the maximum height. How high did that javelin get? Okay. Oh, first I've got to correct for sig figs. There you go. It flew 136 meters. I have 3 significant digits. I have 3 significant digits. I have 4 significant digits. 3 is my limiter. So 136 meters horizontally. Okay. There you go. I'm going to leave that there so I can use that in the future if I need to. So I need the maximum height. Okay. We know the initial vertical composite velocity vector was 28.39084. That's right here. Okay. And that gravity worked to slow that down for its flight upward, which was half the total flight time. Okay, I've already found the 2-point-something seconds for the time that it took to go up. We can therefore use the displacement equation and half the flight time. So here's my displacement. The final velocity was 0. The initial velocity is this number. Okay, and the amount of time that it took to make that happen. So here's my final velocity, my initial velocity, half the flight time that it took to go up, right? And so I just do the math, I multiply, and I get 41.0825 meters. So 41 meters high, 136 meters out. Okay, I need to correct for significant figures again. So the javelin flew 41.1 meters vertically, 41.1 meters up, 136 meters out. Okay, so that is the answer there to the javelin question. If you have questions, if you don't understand it, pause the video, replay that example as many times as it takes for it to make sense. And if you have any questions, go ahead and post them in the comments field, and I'll do the best I can for you. Moving on to another kind of two-dimensional motion. Because velocity is both a direction and a magnitude, if an object stays at the same speed, so the magnitude doesn't change, but it changes direction, then that's also a change in velocity, which is acceleration. Okay, so acceleration is any change in velocity. It could be the change in the magnitude, or it could be the change in the direction, or it could be both. And so we need to be able to analyze any kind of change in velocity. So here we're going to look at another example of changing velocity. By analyzing the component vectors, the acceleration vectors can be found and analyzed. So we're going to do that. Here we have another kind of example. Okay, motorcycles, racing, going fast. And they come around this corner, which is a 120-degree left turn. Now, we're going to assume incorrectly that they keep going the same speed. In reality, they slow down and they accelerate at different parts of that curve. We're going to pretend that they stay the same speed all the way through just to make it simple. Okay, so they are doing about 80 miles per hour or 35.76 meters per second. Okay, and they make a 120-degree left turn. What's the vector of the acceleration if the corner takes them 1.85 seconds to complete? Okay, so we have here the initial vector, 35.76 meters per second at 90 degrees positive. I'm going to make that line up straight on the y-axis so that it's easier to deal with. 120 degrees to the left puts me down here, same magnitude, 35.76 meters per second, but at a new degree of a negative 150 degrees. Now you say, wait a minute, I thought they made a 120-degree turn. Why is it negative 150? Well, remember on a coordinate system, we always measure from the positive horizontal axis. So this was positive 90. 120 degrees off to the left of that is the same thing as 150 degrees going this way. Okay, so that's negative 150 for the sake of these Cartesian coordinates. Alrighty, so we need to analyze this. Acceleration is the change in velocity per unit time. So I have this final velocity minus my initial velocity. So I have the initial velocity here and the final velocity here. I need to be able to subtract those. And then once I've done that, I need to divide by the unit time. Now you may think, oh, that's not too bad. That's 35.76 minus 35.76. Well, but that would be true if it were one-dimensional. We're two dimensions now. We need to look at the x and the y component of both of those vectors in order to be able to do this problem. Okay, so here we go. Let's look at the first one at v sub 1, the initial velocity. It's very easy because I drew my problem to line up right on the y-axis. Okay, so the v1x, the x component of this velocity is 0. It's not moving left and right at all. So that made that easy. The v1y is 35.76 because it lines up perfectly with the y-axis, so all of my velocity is on that axis. So that made that one easy. So we'll just park that one for future. Okay. Now the second one is a little bit harder. I have to look at the x and the y, the x and the y of this line. And I have to keep all my signs correct here. Okay. So v2x is in the negative direction because x going this way is negative. And it's adjacent to the indicated angle, this one here. I'm going to be using the 30 degrees here. Now, again, this is negative 150. This whole thing is 180 degrees, so it's easier to use this part of the angle as 30 degrees than it is to use all of this as 150, okay, for my triangle. So I'm going to use this 30-degree portion, okay, and so this is the adjacent line, so I can use cosine. So the hypotenuse times the cosine of theta gives me this here. So negative 35.76 times the cosine of theta equals negative 30.96907, ridiculous number of digits, meters per second. Okay, so that is this component. And then I need the y component. Same thing, it's in the negative direction, it's going down. So this now, if I were to draw this line over here, this is opposite my angle, so that's the sine. Okay, so now the hypotenuse times the sine of theta is negative 17.88 meters per second. Don't have as many decimal places there because I just can't get them out of this problem. That's as many decimal places as I got. Okay, so that is my y component. Also negative, it's going down. Alrighty, now I just have to subtract. Remember, this is v2 minus v1. So all of the analysis for component vectors that I did was so that I could do this subtraction. Okay, so my acceleration velocity, my final velocity here, is going to be 2 minus 1. So let's look in the x direction and the y direction separately. In the x direction, 30.96907 minus 0, because there's no x direction in the initial velocity. Okay, and in this one we have 17.88 minus 35.76. So I'm subtracting in the x this number minus 0, and in the y this number minus this number. Now watch your signs. This is a negative minus a positive, so I actually get a larger negative number. Okay, negative 53.64, and here it's just the same because this other one was 0. So now I have my final x and my final y. Now I can draw my resultant vector. Okay, so I have, just kidding, there it is. Where am I now? There it is. I have my final x and my final y, and I can draw this now as a resultant vector by combining these composite vectors here. I'm going to use the Pythagorean Theorem to do that because I have two legs of a triangle and I'm looking for their hypotenuse. Okay, so a squared plus b squared equals c squared. So c, the hypotenuse, is the square root of a squared plus b squared. Okay, we're just going to rearrange the Pythagorean theorem in that way. So my x component squared plus my y component squared, both those are negative numbers. When you square them, they become positives. And the square root then is going to be 61.93395. But don't forget that we are still in the negative direction here because both the x and the y were negative. And you could see that too. The square root of a number is actually the positive or the negative, because -3 or 3 squared are both 9. See how that works? So we're still negative here, 61.93395 meters per second. Again, way too many decimal places. We don't round yet. Now we need to find the angle. So I know that this is the magnitude of that line, but I don't know the angle yet. Okay? So we need to get the angle. We're almost done, I promise. We have the x and the y components. So we can use any of the trigonometric functions because we actually have both the x, the y, and the hypotenuse. We could use tangent, sine, or cosine. I'm going to use tangent just because I like it, but you could use any of them and be accurate. Okay? Tangent of theta is the opposite divided by the adjacent. So 53.64 divided by 30.9607 is going to give me 1.73252. So the tangent of theta is that. To get theta by itself, I have to take the inverse tangent of both sides. So theta is the inverse tangent of that number, which gives me 60.00670. Okay, so basically 60 degrees is where this line comes out. Okay, so that's going to be that measurement there. So I can now put all of this together. Okay, I have my final velocity, or my difference velocity rather, v2 minus v1 equals 69.93395 meters per second at negative 119.99333 degrees. Yay, and why that, and why not 60? Well, 60 is this, and remember we always measure from the positive horizontal, so that's going backwards. So this and this makes the 180 degrees here. Okay, hope that makes sense to you. So here we go. This is my difference vector, my difference velocity. I have to divide by time. So 61.93395 meters per second divided by 1.85 seconds, that's how long it took them to make the corner, gives me an acceleration of 33.47781 meters per second squared. And that is the same direction. I don't have to do any more direction. Okay, this difference velocity is the same direction as the acceleration. Okay, so now, yay, correct for sig figs. The bikes were accelerated at 33.5 meters per second squared, and you can see that because that was meters per second divided by seconds, so the seconds in the denominator is squared, at an angle of negative 120 degrees. This number basically is 120. Okay, so that is the final answer. That is the acceleration vector for the bikes that made that corner. Again, if you need to see that again, go back, watch it again, pause it if you need to, ask me any questions below. I'll see you in class tomorrow. God bless you.